Hello, everyone. Good morning, afternoon, or evening. Dear authors and invited guests, welcome to Technical Session 12B. My name is Alesha Mulla, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Conference on Information and Communication Technology for Sustainable Development, ICT4SD 2026 in Goa, India. The 11th edition of the conference is being organized in a hybrid mode. The physical session was held on 9th July in Goa, and the virtual event is being held from 9th to 11th July 2026 via Zoom. I hope you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 10 presentations. Each presenter will be given 10 minutes for presentations and 2 minutes for question and answer. On the 9-minute mark, I will raise a gentle reminder. There is another request to all of the participants. Please stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Before we start the session, I would like to introduce you all to the chair for today's session. Dr. Anupama Kumar is an associate professor in the Department of Artificial Intelligence and Machine Learning at RV College of Engineering, Bengaluru, India, with over 25 years of teaching experience. Specializing in data mining, parallel computing, and data science, she has published more than 32 technical papers in peer-reviewed global repositories. Welcome, ma'am. I request you to please say a few words.
Yeah, hi everyone. All the best to all the presenters. We are waiting for sessions also. All the best to everyone.
Thank you, ma'am. Before we begin, we have to take another presentation. Just one moment. First up, we'll have Chavi, who will be presenting Unmasking the Traitor, Detecting the Dishonest Nodes in Distributed Cyber-Physical Systems for Fair Elections. You may now begin.
Good afternoon to one and all present here. Today, we are here to present our research paper. Our work titles Unmasking the Traitor, Detecting Dishonest Nodes in Distributed Cyber-Physical Systems for Fair Elections. Have you heard about AWS or Azure? Then you already know what a distributed cyber-physical system is. Let's look at this picture, which showcases how all the workers, specifically servers, work to perform a task for the clients or apps. A leader stands at the center to manage the task assignment, workflow, and monitor the overall working. By this, we could clearly conclude how important a leader is. But who elects this leader? Is it the admin? The developer? No, the network itself decides who the leader will be by utilizing a leader election algorithm. Let's look at another image. When a leader fails, nodes start an election. Each node shares its rank through a parent-child network. The parent selects the best candidates and forward them. When the initiator receives the ranks, it picks the best candidate as leader and broadcasts it. Others are saved as backup leaders. So a new one can be chosen quickly without a full election cycle. This was the part of our base paper. But wait, isn't there a problem right here? The blind trust? Each node shares its own rank. How could we say that the rank was correct? To solve this problem, we propose a novel leader election algorithm that flows as follows. Before voting, each node takes a snapshot. It hashes its rank vector and shares the committed hash with neighbors. Then the election tree is built. In phase 3, the threshold vector is revealed, and nodes propagate their actual rank vectors through the spanning tree. Parents verify them in real time by rehashing and checking against the snapshot, instantly pruning any node that cheats. Only the valid data moves forward, and each parent calculates a node's score by measuring cosine similarity between its rank vector and the threshold. Finally, the initiator sorts the list and declares the leader. Another question: does our algorithm work?
So to test our algorithm, we begin by setting up a simulation environment using Microsoft's MS MPI with Python. Each node in the system was represented as a separate process, and random graphs were generated to mimic distributed network. To test the resilience of the system, we deliberately programmed node 3 as a dishonest participant, sending fake rank values during the election process. This allowed us to evaluate how well does our algorithm detects the traitor nodes. The experiment scaled from 4 number of nodes to 30 number of nodes. We used SHA-256 hashing algorithm to commit the rank vectors, ensuring that node could not alter their claims mid-election. Unlike traditional methods that simply selects the highest rank, our approach requires a similarity scoring using cosine similarity against a hidden threshold, making spoofing nearly impossible. Now let's look at the results. The algorithm successfully detected the dishonest node in every scenario. As we can see here, as the number of nodes increased, the total messages also grew. But the growth was controlled. As you can see here, it is less than quadratic. For example, for 30 number of nodes, the message overhead is 330 and not 900, which is less than its square. Execution time generally increased with network size, but interestingly, some larger networks finished faster than the smaller ones, which shows that topology also played a great role in this. Overall, the algorithm maintained the scalability and robustness. The time complexity was proportional to the network diameter, that is O of D, while message complexity is proportional to O of E. Importantly, security alerts were triggered whenever a traitor was detected. In conclusion, we were able to propose an algorithm to ensure accountability and fairness in leader election. By combining cryptographic pre-commitment with vector-based ranking, our algorithm unmasks the traitor and safeguards critical infrastructure. Thank you so much. Now we are open to questions.
Good presentation. Chavi, I have one question. So, what is the base algorithm you have taken to compare your own algorithm?
Ma'am, in the base algorithm, there was no cryptographic commitment or there was no use of cosine similarity. So, our
Okay.
algorithm is novel in this approach that we have utilized commitment procedure and means by cryptographic hashing. And secondly, we have also utilized cosine similarity. In the base paper, there was rank was calculated as a single value, but we are using the full vector. So you cannot
Okay.
just say that my value is this and win the elections.
Okay. And one more question is, see, now the distributed systems have become so advanced and we have map reduce and other such technologies which are taking care of these kinds of work. Correct? So how are you going to justify your work is different from such kind of technology?
Sorry, ma'am, could you please repeat the question?
Okay, nowadays we have distributed and parallel programming which are using MapReduce programs, correct? We
Yes,
have
ma'am.
MapReduce. MapReduce is also doing similar kind of distribution only. So in that case, how is your method better than those things?
Oh, ma'am, I think it's because in those areas we don't use anything like cryptographic hashing. Means we are not checking the ranks value. There is very less work for that, almost negligible. That nobody was checking for the whether the rank was correct or not. We trust blindly on a node. So
Okay.
that blind trust is not valid. We wanted to remove it from this phase. That's why we utilized it.
Why did you select Python?
Sorry.
Why did you select Python for this?
Python, because Python is a it's a very quick interpreter required language. It was easier to implement. There were libraries available because MSMPI
Uh,
was easily workable with Python. Quick library was available.
okay, Jimmy. Good work. Good work, Jimmy. Thanks.
Thank you, ma'am.
Thank you, Chavi. We'll now move on to the next presentation. Our next presenter for today is Vedant Kaushik, who will be presenting a multi-tier hybrid architecture for efficient and explainable DDoS detection using ensemble learning. You may now begin. Is Vedant or any of his co-authors present in the meeting? All right. In that case, we'll move on to the next presentation. Our next presenter for today is Simran Yerave, who will be presenting a sentiment-driven machine learning approach to stock price forecasting in Indian financial market. You may now begin.
Hello.
Yes, Simran, you're audible.
Okay. Good afternoon, everyone. My name is Simran Erwin. Today, I am presenting our research titled A Sentiment Driven Machine Learning Approach to the Stock Price Forecasting in the Indian Financial Market. This work was carried out with our co researcher Ayush Tiwari, Nikita Ganaj, and Kanika Kumawat under the guidance of Dr. Nicholas Joshi at the Thadumal Shani Engineering College. Our research explored whether combining historical stock price data with a financial news sentiment can improve the stock price prediction compared to the traditional forecasting methods. Introduction. Stock price in the Indian market are influenced not only by the historical price trend but also by news, company announcement, earning reports, and government policies. Investors react to this information almost immediately, which affects the stock price. However, traditional forecasting models mainly rely on historical price data such as open, high, low, close, and volume. While these models identify pattern in past price, they ignore one important factor, that is the investor sentiment. Our research aimed to bridge this gap by combining the market data with a sentiment extracted from the financial news. Literature review. Literature. Next slide. Okay. We review three main approaches used for stock prediction. The first includes statistical methods like ARIMA and linear regression, which are simpler but assume market behave in a linear manner. The second include machine learning algorithms such as SVM, random forest, and gradient boosting, which capture complex patterns but still ignore the news sentiments. The third uses NLP models like Finbit, which analyze financial news and determine whether the sentiment is positive, negative, or neutral. The research gap we identify is that very few studies combine the price data and sentiments together, especially for Indian stock market. This is what our research focuses on. Our objectives. Our study has three objectives. First, to build a sentiment based stock prediction model that perform better than the price only model. And second, to evaluate how much investor sentiments influence short term stock price movement. And last, the third, to support both daily and hourly forecasting, making the model useful for both swing traders and intraday traders. Next slide, methodology. Next slide. Methodology. For our dataset, we collected nearly 5 years of historical stock data from 10 major NSE listed companies across different sectors. Along with price data, we collected financial news articles. We used FinBit, a transformer-based NLP model trained especially on financial tax, to classify the each news article as a positive, negative, or neutral, and generate a sentiment score. We then created additional features such as moving averages, momentum indicator, rolling volatility, lagged price values, and rolling sentiment averages. Finally, all these features are prepared to our CatBoost machine learning model, which learn the relationship between market data and investor sentiment to predict the future stock prices. Next slide. The system architecture. The system architecture of the research has two main important pillars. That is, the first, collect the stock price data using Yahoo Finance, while the second, collect the financial news through News API. The news is analyzed by Filbert to generate the sentiment score, and this score are combined with the stock price features. The combined data is then processed by CataBoost and will generate the stock price prediction. And the results are displayed on the dashboard through a backend where the user can view the predictions and the sentiment insights. Next slide. The results, our model perform well for both daily and hourly forecasting. For daily production, it achieved 87.27% directional accuracy with a MAP of 14.32%. For hourly production, the accuracy was 82.38% with a MAP of 17.15%. Although our hourly accuracy is slightly lower because of higher market noise, and the RMSE is lower since the hourly price movement are much smaller. We also analyze the relationship between sentiment and stock returns. Next slide. Here, the relationship between sentiment and stock return. When the sentiments are bearish, the average next day return was positive 1.4%, with production accuracy reaching 88%. For neutral sentiment, the returns were around positive 0.2%, while the bearish sentiment resulted in an average return of negative 1.2%. This result clearly showed that the investor sentiment has a significant impact on a stock price movement. Next slide. Key findings. Our study produces three important findings. First, incorporating the sentiment analysis, improve the production accuracy by 6 to 9%, especially during earning announcements and major market events. Second, our combined model achieved 88.6% directional accuracy, outperforming the price only model at 82.4% and the sentiment only model at 71.1%. Finally, the sentiment trends for individual company closely matches their actual stock movement, to confirming that the investor sentiment is a valuable predictor of a market behavior. Next slide. To conclusion, our research shows that combining the Finbit-based sentiment analysis with CatBoost model improve the stock price prediction compared to using the historical price alone. Thank you for your attention. I will be happy to answer any question.
Good presentation. Can I have details about your data set? From where did you collect the data, and what are the features you had? What did you do feature extraction?
We actually collected the financial data, that is the historical data from Yahoo Finance, and news, financial news from News API.
Okay, what type of noise did you find in the data when you are doing feature engineering? Because when I'm saying I'm collecting financial data, there might be some noise in when you're real time when you're collecting the data. And how did you manage the streamline of the data? If it's real time, you will be getting a lot of noise in the data and there will be a lot of hiccups when you're collecting and processing. How did you handle
Missing news on a given day for a stock replication or an out of order timestamp. The individual outlier articles are Steve and Daily Sentiment. So the missing news is handled by carrying forwarded last known sentiment score instead of leaving a gap, and the duplicate are by removing the duplicates times and keep the data in a strict chronological order before alignment, and the hourly specific type of handling is by adding resampling and session normalization.
Okay, thank you.
Thank you.
Thank you. We'll now continue with the next presentation. Our next presenter for today is Shrishnav K, who will be presenting Adaptive Zero-Day Threat Identification with Unsupervised Machine Learning for Robust Cyber Defense. You may now begin your presentation. Is Shrishnav or any of his co-authors present in the meeting? All right. In that case, we'll move on to the next presentation. Our next presenter for today is Sayeda Imtiaz, who will be presenting AI-enabled ever-watched muffled distress sound detection system for women's safety. You may now begin your presentation.
Yes, I will share my screen.
Yes, please.
Are you able to see my screen?
Yes, we can.
Okay, thank you. Hello everyone, I am Imtiaz and I am here to present our paper. Title is AI enabled Everwatch muffled distress sound detection for women's safety. So I will be covering the our problem statement, objectives, then project planning, design, dataset design. Okay. Uh, for giving you an overview of the problem statement, our project is for women's safety system. So most of the existing safety system and audio classification research works mainly designed for clear speech or keyword based emergency detection. Like they would want the victim to create the sounds like help or manually pressing any buttons, they will be giving the emergency buttons, but their focus is like detecting onto the explicit words, loud screams, or clearly audible signals. These systems assume that during an emergency, the victim is capable of creating the detectable sound. However, in if you are considering the real assault situation, this assumption often fails because the victim may be forcefully silenced, and in such cases, the only source of sound that will come out will be the muffled sound. Like when someone is forcefully suppressing your mouth, like the sounds like this, hmm, kind of sounds, they are the only source of sound present there when someone is in a danger situation. So, our objective was to detect these kind of the sounds, and which will be really helpful for especially for the women in the danger situations. Our objective was to develop an AI-based system capable of detecting these sounds, enhance the personal safety, and create an automated alert system, which covers the scope like our AI-based mobile application. I will give you an overview of the overall project design. We created a mobile app which will be continuously doing the voice monitoring, and this voice monitoring will be voluntarily taken. Like if the user is going out, then he or she can turn on the background audio detection, and then comes the main our module, that is the model voice activity detection, which will be continuously detecting those sounds, and if distress sound is detected, it will be taken action like location tracking system, and it will be sent to the emergency contact. And this is usually the many of the existing systems will be having, like location tracking, sending messages to the contact, but our main focus is in here voice activity detection. So we did the literature review when we were reviewing the past work in this area of audio classification and safety systems. We found that mainly the papers were focused on to heavy breathing, or someone is running detecting depending on to the footstep sounds, or they are calling for the help words, screaming loudly, crying, and none of their focused onto the muffled sounds. And when we were trying to find the data set which were focused onto these muffled sounds, we found like very less sounds or none sounds which are focused on data set which are focused onto this kind of the sound. Like there are major data sets like free sound and Google audio set, which has many different sounds like environmental sounds, and they also had the crying sounds, heavy breathing sound, but muffled sounds were not there. And this indicates that this area is very underexplored research area. So we created our own custom audio data set. Like among them, 25 to 30% we team members, we produced by ourselves. We recorded our voice using microphone, and other 65 to 70% of the samples were collected from the major time consuming part for this research was collecting the data set only. So we gone through the movie clips on YouTube and screen recorded those parts where the user is forcefully getting silenced. So we screen recorded those, converted them into the audio, and we collected around 360 samples like this. And for non-distress sounds, for the classification, environmental sounds like bird sounds, traffic sounds, or normal human talking sounds, we used Google audio set for that. And for keeping a balance, we took only 1000 samples for the environmental sounds. So now comes the pre-processing part. As our input is an audio signal, we needed to convert them into the spectrograms. And normal speech generally contains the stable vocal patterns like clear phonetics and strong high frequency details. But when a person's voice become muffled due to suppression, like covering of the mouth, what remains are unstable breathing bursts or compressed vocal textures and low energy and irregular pressure patterns. So the challenge in our work is not simply speech recognition, but to preserve and detect these subtle distress acoustic that still survive after the suppression. And because of this, we like realize that directly applying the standard speech processing pipeline may not work effectively for our problem. And most traditional pre-processing method treat the entire frequency spectrum equally because they are optimized for clear speech recognition tasks. But in muffled distress detection, all frequency regions are not equally useful. Like the higher frequency speech details becomes unreliable after muffling, while the low and middle frequency regions still preserve this important distress information. So our contribution was to uh, do a distress aware feature extraction approach. So instead of simply generating a standard mail spectrogram, we modified the extraction process specifically for muffled distress acoustic. And like we also introduced a distress oriented weighting concept. Generally, the distress male spectrogram would be featured like S-mail, F of T, like with frequency and a time comparison. But we tried to giving weights to this frequency spectrum, giving higher weights to the low and middle frequency region and lower weights to the high frequency region, so that these distress sounds could be covered and will be preserved for the detection. So those raw audios were sampled for uniformly keeping the 16 kilohertz. Then we trimmed all the audios to the 3 second windows, keeping them uniform. And we followed those process pattern to applying the windows onto it and converting them into the mail filter bank. So the final mail spectrogram would look like an graph or an image pattern of frequency versus time. Then we used a lightweight CNN based model. This is the general training approach, because our main focus was on to the feature extraction and data pre-processing. So we trained a lightweight CNN model to classify the sounds, and we use CNN because CNN is majorly used for the image kind of the input, and our uh, final processed data was in the form of the image, which was showing the value of the signals in comparison of frequency versus time. So we evaluated the performance and optimized them and exported the model into TensorFlow Lite as we were creating a mobile application for it. So these are the results. Our accuracy was around initially we used the first we were doing the trial and error method. We followed the standard sound processing approach, and our frequency was around 70 or 65%. Then we did the weighting based approach, and we found some good result of around 98%.
Excuse me, I'm so sorry to interrupt. You have 1 minute left.
Okay, sure. I will quickly go through the remaining part. So we created an Android app for it. You can see it. We gave the user two options of like when they want to start this directly voice monitoring. If they like when they are in home, they can turn it off, and when they are going outside, they can voluntarily then turn it on. Yeah, these are the screenshots of a mobile application. Yeah, so this project successfully demonstrated that we created an AI based safety system for properly detecting those muffled sounds. And the future scope would be like we got the accuracy of around 98%, but we think that we did not we might not have a proper balance in between the distress and environmental sound. So future scope would be increasing the data set for collecting variety of the sounds into the distress samples. And yeah, yeah.
Yes, you people have done a very good job. My only question is, you told you have applied CNN. Why CNN?
CNN, because our input is a male spectrogram, which is like an image of the audio. CNN is very good at finding patterns in the images. So it learns breathing patterns, muffled cries, and vocal strain automatically. It also gives a good accuracy. Also, the one of the major point as well we selected CNN is because CNN is a lightweight model for mobile deployment as well.
Okay, one more question. What is the size of the audio which you people have taken for work? Is it a standard size for all the videos, or each video set has a different size for muffling? So
Sorry,
somebody has muffled
size
size of
of
your audio, size of the audio,
size of the
size of the audio. Ah,
like each audio sample was standardized with a fixed length
ah,
of 3 seconds, and
ah.
all recordings
Okay,
were resampled to 16 kilohertz. So each audio
okay,
contains around 48,000 samples, and this gives a uniform input size for feature extraction and model training.
okay, okay. Good presentation. Good work. All the best.
Thank you.
Thank you, Imtiaz.
Yeah.
You may now stop presenting. All right. We'll now move on to the next presentation. Just a moment. Our next presenter is Rohan Joshi, who will be presenting content-based movie recommendation system using Feature Fusion. You may now begin.
Yes, ma'am. Is my screen visible?
Yes, it is.
Okay. So, good afternoon, everyone. Myself, Rohan Joshi, and today I will be presenting on a paper titled Content-Based Movie Recommendation System using Feature Fusion. So, my team is Karan Singh, Dev Tanali, Lukman Sheikh, and also we made it under the guidance of Ikta Savra. So, today I will be presenting it alone because of the job. So I will begin. So our work focuses mainly on improving movie recommendation system by combining multiple movie features, basically the metadata such as rating, runtime, and genres, also the cast information, to generate accurate recommendation system without relying on user history. So with the rapid growth of streaming platforms like Netflix, Amazon Prime, thousands of movies are available online. This abundance of content often makes it difficult for users to find movies that match their interests. So our recommendation system basically solves this problem by suggesting relevant content to those users. There are three existing recommendation approaches: collaborative filtering, content-based filtering, hybrid recommendation. So we chose content-based. Why we choose content-based is because it doesn't have dependency on users' interaction. Also, it provides better privacy and security to for users' information. Solves the cold start problem for new users. And works well with limited user interaction. So, our problem statement is basically, although recommendation systems are widely used nowadays, they still face several challenges. Cold start problem, sparse user rating, poor recommendations for newly added movies, also heavy dependence on users' interaction history. So, most previous work focus on collaborative filtering and deep learning models, which require huge data sets. So very few focuses on metadata processing, metadata being rating, movies metadata, and feature fusion, lightweight recommendation model, and efficient similarity computation. So we reviewed several existing approaches, such as Pazani and Bils's proposed content-based filtering, similar to us, but they used limited feature representation. Burke's approach was hybrid recommendation, but it had also higher complexity and had decent accuracy. Char similarity metrics didn't focus on pre-processing of dataset at all, while Kim's CNN recommendation required large amount of datasets. Our proposed work was basically combining feature fusion and cosine similarity to better work better with small to mid-scale datasets. So our main objectives are to develop a content-based movie recommendation system, perform effective pre-processing of movie metadata, to fuse metadata features such as rating, runtime, genre, and cast, and to improve recommendation quality while reducing the dependency on users' history. We generate recommendation efficiently in real time. Our proposed methodology is basically, first we collect metadata containing title, rating, runtime, genre, and cast. Next, the data is pre-processed by filtering non-English titles, normalizing the runtime values, basically converting the time span of a movie to a minute, from hours to minute, and encoding genres using multi-out encoding. Multi-out encoding basically converts genres what are available in a movie to a numerical form. Consider an example of Inception, which has action and drama and sci-fi, and doesn't have fantasy or war or any other stuff. So it will give 1100 such type of numerical vector. One is for what exists in the movie, and zero is what does not. Then these numerical, categorical, and textual features are fused into unified vector. We also use TF-IDF vectorizer to convert cast into a numerical form so that we can use that to create the unified feature vector. Using the feature vector, cosine similarity is calculated between the selected movie and all the other movies. Finally, the movies are ranked according to their similarity score, and top 5 or top 8 most similar movies are recommended. Our dataset consists of 2000 movies. We collected it from IMDb, TMDb, and also the Kaggle. We normalize the rating from between 0 to 1. We normalize the runtime into minutes, and converted a genre into a numerical form using multi-word encoding. We removed missing and inconsistent records, also converted the top 7 cast members into a TF-IDF vector. The characteristics of our experimental data basically it talks about what data set we have, what are the characteristics of the data set we use. So our data set consists of 60 to 80 rating, most of it. Most of the movies are between 80 to 120 minutes of time span. Also, we had more drama, comedy, romance movies in our data set. Uh, and this is our result. Basically, I typed in our website, Inception, and I got similar sort of movies, sci-fi movies, etc. We used these metrics to calculate the accuracy of our model. We used ASS, which calculates the similarity between the queried movie and the recommended movies. We also calculate the diversity in the recommendation list. Also, we calculate the genre occurrence, how our queried movie and the movies recommended have similar genres. As you can see, in a random approach, the diversity is quite high. While if we consider a model just based on the popularity, the diversity is still high, but average similarity score has just rose. While in genre matching, the average similarity score, also the genre occurrence is quite high, and ILD is less. While in our method, we provide both genre coherence, also the ASS score with less ILD. So in conclusion, we developed a content-based movie recommendation system using feature fusion of rating, runtime, and genre and cast information, of course. Uh, by applying pre-processing techniques like multi-hot encoding, TF-IDF, and cosine similarity, our system generates accurate and efficient movie recommendations. The proposed method achieved an average similarity of 0.81, and 78% of our catalog was covered in each and every record, and maintain a good balance between relevance and diversity. The proposed approach is efficient, interpretable, and suitable for real-time recommendation system without relying on user interaction history. Future work includes incorporates plot summaries, director information. Other than cast, we are planning to take in others, writers, directors, also in our consideration. We are planning to implement deep learning models as well to make it a more hybrid approach. Thank you.
Rohan, what is
Yes.
novel in your project?
Sorry, ma'am.
The recommendation systems in the market, right?
Hmm. Yes.
So what is novel in this work? And from you have mentioned that you have collected data from IMDb and other sources. Correct? So what is that
Yes.
particular feature extraction technique you have implemented in this project?
So, ma'am, in Netflix, they are heavily dependent on collaborative filtering. They use other users' information to recommend other users based on those recommendations. We, but for new users, like if they are entering, new users are entering in our website, there is their problem is cold start problem basically. Cold start problem is like the user doesn't have history yet as of yet. So what recommendation do they provide? So basically, they won't provide recommendation based on the user's interest right now. So we just take minimal information from user and provide a better recommendation than that. We are planning to incorporate the users feedback as well, but as we have seen, there is past user feedback in this industry. Like not many movies have feedbacks, all the feedbacks. Quite few feedbacks are there for a particular movie.
No, no. What do you mean by past feedback? Say, for example, I am
Yes,
interested in watching action movies. Correct. So in
yes.
that case,
Hmm.
what I'll be doing is whenever there is a recommendation option given to me, I'll be opting
Hmm.
it good or like, or I'll keep on doing it. Are you mentioning this as a past feedback, or are you going to check out for what are the different types of movies I am watching, or how many times I am watching it?
Ma'am, you just
How
have
is
to
that particular data
So, ma'am, you
taken in?
just have to input a movie that you have previously watched. Like if you have watched Avengers, so you can
Okay,
just input it Avengers. You liked it. If you liked it, you can input the Avengers, and you will get similar recommendation based on that.
okay.
You will get Tron Legacy or Iron Man 2,
Mm-mm.
something
So
with your
your
request.
system along with movie recommendation, are you focusing on the sentiment analysis of the movie also? How many customers or how many people are viewing such kind of movies also?
Uh,
Or
yes,
it's
ma'am.
only recommendation system?
It's only recommendation system, ma'am. We just consider the ratings. We just consider
Okay.
the cast members of the movie. We
Mm-mm.
consider genre coherence. Genre coherence is important here, and yeah, that's we consider those. Uh,
Okay.
yes,
Okay,
ma'am.
ma'am. Good one. Good one.
Oh, thank you.
All right, we'll now move on to the next presentation. Our next presenter for today is Katleho Mohoje, who will be presenting Designing a Human-Centered Augmented Reality Extension for a Digital Twin Architecture in Smart Manufacturing. You may now begin.
Can you hear me?
Yes, we can.
Okay. Can you see my screen?
Yes, we can.
Okay. Good afternoon, everyone. My name is Katleho Mohoje, and the title of this study is Designing a Human-Centered Augmented Reality Extension for Digital Twin Architecture in Smart Manufacturing. In the late 1990s, physical and computational processes became too tightly coupled due to factors like data processing demands and rapid scaling of network embedded systems, giving rise to cyber-physical systems that later became foundational to the Industry 4 revolution in smart manufacturing. Automation is the baseline capability that enabled machines to perform repetitive physical tasks. In turn, this reduced the presence of human intervention on the factory floor. Cyber-physical systems globalize the factory floor context by bridging the individual controls that drove automation to software networks. This coupling of physical and software processes improved scalability and enabled real-time interactions. The Industry 4 revolution, amongst other outcomes, accelerated widespread adoption of cyber-physical systems. One logical manifestation of this is the digital twin. It acts as a virtual replica of physical processes on the factory floor. Its bidirectional communication enables successful preventative maintenance through simulations and advanced diagnostic frameworks, amongst other capabilities. One drawback identified by pioneers of Industry 4, as mentioned, is the reduction of the human presence on the factory floor. Spotting economic and industrial ramifications, the next industrial revolution, Industry 5, is changing the human disposition. identifying the human as a critical component in smart manufacturing. The enduring conquest of automation keeps smart systems constantly on the move, creating latent design oversights that require human intervention. Industry 5 introduces human centricity as a philosophy that utilizes smart systems to complement, protect, and enhance human capabilities on the factory floor. Building control architecture, co-robotics, and smart interfaces that match and enhance human capability based on this philosophy. We can define this as human-centeredness. To achieve the Industry 5 mandate, a design that complements the existing architecture of a digital twin within a cyber-physical system is proposed. This system utilizes augmented reality to enhance operator diagnostic capabilities by overlaying virtual data directly onto a real-time video stream. Malta et al. Suggests that this integrated overlay approach increases both visual attention and cognitive performance during diagnostic tasks. Because sensing, control, and feedback became automated in Industry 4, human involvement at low levels decreased, with operators primarily responding to unplanned mechanical downtime, while digital systems successfully managed routine preventative maintenance tasks. The unplanned downtime shifted into information layer. For example, electrical instability to software can propagate as signal distortions, control misclassifications, and timing irregularities amongst a few. While diagnostic dashboards excel at steady-state monitoring, pipeline instabilities that cause signal bursts or cascading logs can interrupt data flows and freeze or delay instrumentation, which in turn compromises downtime resolution. This is further increased by the degradation of human trust in the system and the interpretation of the data. Unplanned downtime is traditionally framed as mechanical failure. However, in a cyber-physical environment, a machine can be physically powered on and justifiably operation, yet incapable of performing its intended function due to perhaps a frozen display or delayed data stream. This relates to how the International Organization for Standardization, specifically Standard 22400, formalizes functional unavailability through operational capability and not physical uptime. This study quantifies data latency as functional unavailability, enabling the ability to calculate visual interface delays as unplanned downtime. Industry 5 mandates human centricity, but modern systems tend to ignore human cognition and fail to track how fast operators receive critical data. The underlying issue is a hidden form of informational unavailability or unplanned downtime, where a machine is powered on but falls short because of temporal data infidelities that paralyze the operator's ability to act. At the time of this writing, limited research led to the investigation of a lightweight dual pathway edge architecture. The idea is to bypass routine telemetry bottlenecks from the cloud or internal pipelines, delivering to the user faster diagnostics during routine or emergent cases. The goal is to reduce the time between fault occurrence and fault display and improve visual stability in order to mitigate unplanned downtime. The framework is evaluated using a water bottling plant case study at the Central University of Technology in Bloemfontein. It utilizes a mixed model stochastic assembly line driven by a digital twin, originally deployed by Chawlala to reduce cycle time. The environment features 3 SMUs or smart manufacturing units for bottle filling, bottle capping, and packaging. In the total downtime decomposition, the focus on what we define as T-render or the interval to refresh and render stable information. Because of this study, the focus is between fault occurrence and visual appearance. Bidirectional control is not required. This experimental setup replaces the bidirectional digital twin with a monodirectional digital shadow triggered via a binary switch configuration on an ESP32 microcontroller. The binary switch together with the ESP32 form the source of truth, representing the SMUs on the factory floor. A signal instance is routed via an MQTT broker to a Raspberry Pi, acting as the local edge gateway. At this edge gateway, the data path is bifurcated into 2 distinct parallel pipelines. The first is the standard MQTT over TCP pathway for secure, reliable data transfer through Node-RED to the MATLAB interface recorded as the baseline. The second path utilizes an MQTT to UDP bridge to stream data directly into Unity for the lightweight augmented reality emergency arm. The broader study encompasses 6 diagnostic tests. However, this phase focuses exclusively on test 1, visual fault response latency, to verify architectural differences and system priority. This measurable performance gap is utilized as the baseline proof of concept. How test 1 is designed is when a fault is triggered on the ESP32, the Raspberry Pi bifurcates the signal to both pathways simultaneously. Both user interfaces are displayed side by side and recorded at 60 frames per second. The footage is then analyzed frame by frame to determine exactly which system reaches visual stability first. In the first test, T1, frame 680 is established as the baseline reference point. Both systems render an all systems nominal state. On the left is the lightweight augmented reality interface rendered in Unity. On the left is the lightweight augmented reality interface rendered in Unity. On the right is the MATLAB Simulink front-end instrumentation. While various alternative technologies could have been used, this configuration serves as a representative baseline for comparison. Results indicate that the augmented reality interface reached its first stable visual refresh frame at frame 694. In contrast, the MATLAB interface required a nearly full second, reaching stability at frame 739. By bypassing the routine remote and internal pipelines, the architecture provided an average visual lead of just 756 milliseconds back to the operator. Across 5 experimental trials, the AR interface achieved the mean visual stabilization latency of 243.38 milliseconds in comparison to the represented digital twin baseline that resulted in 1020 milliseconds, representing a full second delay. The frame-by-frame video analysis isolates the drivers of visual latency. The digital twin's delay is driven by heavy dashboard processing and cloud polling connection overhead, bypassing the bottlenecks via direct lightweight pipeline. This demonstrates the clear potential to close this operational gap.
Excuse me, I'm so sorry to interrupt. You have 1 minute left.
No problem. Future work involves executing the remaining experimental tests to fully map the overall system behavior. Second, establishing a formal testing framework to optimize the emergency arm network protocols. Lastly, an augmented reality global view, applying foundational visual attention and saliency principles pioneered by the likes of Traceman and Azuma to optimize human cognitive processing. This phase illustrated that a lightweight framework successfully complements a standard digital twin. It is coexistence, not competition. Both systems serve a distinct operational role. The digital twin ensures connection-oriented reliability. The AR arm provides stateless real-time speed. Ultimately, balancing these protocols creates a true symbiosis between human and machine. I would like to thank the Central University of Technology for supporting this research and the conference organizers for providing this platform for us to present and discuss our work. Thank you for your attention. I welcome any questions.
Very good work. I have only one doubt. See, all the components which you are talking, or all the softwares which you are talking, whether it can be Unity or a digital twin part, or it's a Raspberry Pi, everything is, I feel they are not in open source, and some of the features of Unity may not be available for us as open source. We have to pick up the license work on it. How far do you think this is financially possible when I go in for a long-term production?
Okay, thank you for the question, ma'am. So as an experimental setup, obviously I was using those kind of components like the ESP32, the Raspberry Pi, and Unity. But for a long-term production process, for example, using Unity won't be a good idea because it's got its own internal pipelines that will cause its own blockages. So this is just for the experimental setup to prove the proof of concept. But when it gets to now the real water bottling plant, we'll probably use tools or technologies like, SCADA and the other technologies that have less latency in them.
Okay, thank you.
Thank you.
All right, we'll continue with our next presentation now. You may stop sharing. Thank you. Our next presentation for today is by Rahul Dhaigade, who will be presenting Developing and Implementing a Competency Modeling Approach in Indian Orthopedic Healthcare Settings, an empirical assessment of medical practitioner roles. You may now begin. Is Rahul or any of his co-authors present today? All right. In that case, we'll move on to the next presentation. Our next presenter for today is Shlok Raval, who will be presenting Investor DNA, a multidimensional behavioral finance framework for AI-driven psychological profiling and mutual fund recommendation. You may now begin your presentation.
Yeah. Am I audible?
Yes, you are.
Okay, I'll just share my screen. Is my screen visible?
Yes, it is.
Okay. So, good afternoon, everyone. I'll be presenting on my project on Investor DNA, which is an AI-powered behavioral finance for profiling of investors based on their behavior and for mutual fund recommendation. So this project was developed by me, Prathamesh, and Ayush, and we have our Professor Swati Vaishnav as our mentor. So before going into the technicalities, I'll just give you a gist of the mutual fund industry. So the Indian market has over 180 million mutual fund folios with a massive SIP inflows, but there is a mathematical disconnect between them. So the average SIP lasts just 3.2 years, but however, an Indian equity fund typically takes around 3.8 years to recover from a 20% market drop. So this means that the retail investors are panicking and selling at the right time when they should be staying in the market. So talking about the conventional tools, they try to fix this with a basic questionnaire that gives you a single static risk score. But this approach is flawed as it collapses with the distinct psychological traits like the panic propensity or maybe the loss aversion into one useless bucket. So talking about the objective of our study, so we broke it down into 6 technical goals. So the very first was like formalizing it in a 6 dimensional taxonomy. So we created 6 different dimensions named passive, preserver, friendly, follower, independent individual, active investor, strategic navigator, and passive investor. So these are the risk. So these are the profiles which we created for the investors. Then we designed a compact psychometric instrument, which is like a 20 questions questionnaire, which could be completed under 6 minutes. And based on this, like we report the dimension to the investor. The third one is like a deterministic DNA coder. So this is a rule-based coder where we map the responses of the user to the mutual funds. And fourth step is basic. The fourth step is basically the fund DNA universe. So we have like as it is a prototype. So we have included 49 equity funds, debt funds, and hybrid schemes. And we also map it to the same 6 dimensions. The fifth one is the implement explainable matching. So we have assigned the cosine weighted score to it, along with SHAP to tell the investors that why we are recommending this and why we have mapped a particular fund with you in which they can invest. And the last one is a grounded LLM advisor, which is basically a Claude wrapper as a chat box. So talking about the existing research or the literature review, so we started by looking at the existing research in behavioral finance concepts like the prospect theory, which states that the losses feel 2.25 times worse than the gains. So which is a well-known fact in the industry, but it is rarely coded into the consumer products. And the existing risk scales erases critical data by collapsing scores. Even the explainable AI models like SHAP are almost never shown to the retail investors. And finally, the LLM chatbots are also hallucinated because they aren't strictly grounded. And our project exactly bridges all of these four gaps. So talking about the diagram, so basically this is the evaluation of the robo advisors. So in generation 1 it is used as a single risk score. In generation 2 and 3 uh, it uses 3 to 5 different discrete buckets, sometimes even a chart linear to shown it to the retail investors. So investor DNA, our project basically moves completely away from the static buckets. We map users onto a continuous six-dimensional vector space, which we pair this with a sharp explainable matches and a grounded plot advisor, along with a smart SIP algorithm to adjust investment based on the market sentiment. Like, it's a well-known fact in the industry that when a market goes down, investor investors should be continuing with their SIPs, and even if the market falls by like around 20% or maybe 30%, like what we have seen in the recent time, it's a best opportunity for them to step up their SIP, basically increase their SIP amount. But it is not done because the investors fear on losing out their invested capital. So we also support investors by these advisories. Talking about the assessment to the dashboard, like from the complete pipeline. So the user starts with the 20 questions assignment. Then so then they are based on those assessment, the user has been classified into the six categories, and then those are mapped with the 49 funds. And from that we tell them, using a recommendation engine, which is a rule based recommendation engine, that what are the funds they should be looking for to invest in. And then we also run a Monte Carlo simulation, like basically we backtest on the tenure selected by the user, 5-10 years, that if they have invested in these funds either from since the inception of the fund or maybe like 2 years or 3 years, then what would the returns they would have get. Then there is the smart SIP signal. It is based on the markets, like how the markets are performing, and whether the investor should step up their SIP or not. And then the investor can also talk to Claude chatbot, and then there is a final dashboard regarding like what are their SIP amount and what are the fund performances after that and what are the returns. So talking about this six-layer system architecture. So in this, like for the front end, we have used Next.js 15 and React. For the state and session layer, basically we have used ZooStand and a local storage. We have used a local storage because the data which the user provides is uh, is very much private, so we can't outsource anything. For the APIs, we have used Fast API and Python. For the AI core, like which is the core of our project, we have used a DNA engine and a mapper along with SHAP and a Monte Carlo simulator and a Claude wrapper. For the data layer, we have extracted the data from the proxy websites such as Value Research or maybe the funds uh, SID, which is like a scheme related information document, using Beautiful Soup and Cache parser. And for the infrastructure, we have used Node and Python. So this is the same. And this is the working which I have explained earlier. Talking about so these are our results. So basically the chart which you are seeing on the left of your screen is basically for a investor who is being classified into strategic navigator. So according to his responses, like based on those 20 questions, these are the mutual funds in which he can invest, along with the On the right, you can see the sharp value. Like why we are recommending these funds is because on his risk tolerance alignment, which is very much higher on a 23, then his panic score guard time horizon, like he wants to invest for more, like 15 years, along with the diversification fit, like he wants to diversify his portfolio and with his growth appetite.
Excuse
And we
me.
have done.
I'm so sorry to interrupt. You have 1 minute left.
Yeah, sure. And this we have done using a sample of 42. So we have basically given our parents and our relatives and our classmates to use this platform, and this data is taken out from them. So, talking about the numbers, so basically our smart SIP has done that whether the when the markets are low and if the investors have stepped up their SIP, or when the markets are not performing, they have reduced their SIP. It has given a better XIRR of around 13.18% than the usual flat SIP when an investor just continues with the SIP amount and doesn't step up or step down. Talking about the technical impact of a project, so this full behavioral pipeline is complete can be done under well under 100 ms milliseconds. And talking about the behavioral impact, so we have removed the panic resistance dimensions, which cost like around 7.8% of points with the top three recommendations of our mutual fund portfolios. Talking about the advantages is basically we have done multiple multi-dimensional profiling, which is a continuous six dimensional vector analysis, which uh, which is very much important because currently in the wealth management industry, the practice is that when a wealth manager asks you about your risk profile, he assesses it only once, and then they recommend the portfolios, and then your risk profile never changes. But your risk profile changes according to your age. When you are like younger, like maybe 20 to 25 years, then you have much more risk to take as compared to when you grow older. And we also have a sharp based linear matcher, which is very much transparent. But talking about the limitations of a project, so we have currently just 49 curated schemes. Along with that, we have basically a rule-based mutual fund matcher, which we are planning in future to replace it with a supervised XGBoost machine learning model. Talking about our real-world application, so this platform can be used by the wealth management in the companies, maybe like for corporate retirement planning, or maybe for an investor to gauge what are their behavior, what is his behavior profile, can be used by a wealth coach training, or maybe like just as a financial literacy tool. So these are our matrix of our platform, which is like we have received, like in case of personalization, out of 5 we have scored 4.61. Overall pilot satisfaction, like according to the people who have used our platform, they have rated us at 4.58 out of 5. And we have complete end-to-end pipeline latency of less than 100 milliseconds with a cloud hallucination rate over just 1.8%. So yeah, I would like to thank the ICT team and the speaker to let me present my idea. Thank you.
Good presentation. How many people did they survey your platform? How many people used your platform? You have shown me a metrics on the range of 5. So I just wanted to know how many customers were there, how many people they used the platform.
Okay, ma'am. So it's just a prototype. So we have let our family, friends, and like various people we know. So there are total 42 people who have used the platform, apart from those who were developing it. So this data is based on the 42 users.
Did you people do any survey before you start the project?
Yes, ma'am. So
did you collect data?
Yeah. So there's for the literature review, like any survey, what we did was basically that we have used multiple we went to multiple companies, like the wealth management companies, and we just asked them like what kind of practices they follow, before starting getting an investor onboarding for an SIP. So they basically gave us the point, and then we designed this overall idea. So basically,
You
what
did
they,
not
as
develop
I,
any.
sorry,
Continue.
yeah, yeah. So basically, what we did was, like, they told us that before starting their investments, they go to the investors and they ask them few questions, like around 3 to 5 questions, like what they directly ask them, that what is their risk score and what are their existing investments and what is their age gap and all. But talking about the questionnaire which we designed, so that was basically based on five main areas. So the very first was like what if someone has like if in your peer has got more returns than you in the same asset classes, then what would you do? Like whether you will be, yeah, will you feel like a FOMO or something else? So those are the type of questions which we have also included in our questionnaire.
Okay, good. Thank you.
Thank you, ma'am.
Thank you. We'll now move on to the next presentation. You may stop sharing your screen.
Yeah.
All right. Our next presenter for today is Neha Chabra, who will be presenting IoT-enabled automotive performance monitoring and driver behavior analysis using ELM 327 and big data analytics. You may now begin. Is Neha or any of her co-authors present in the session? All right, in that case, we'll move ahead with the next presentation. One moment, please. Our next presenter for today is Arya Madhavi, who will be presenting MedExplain, a hybrid explainable AI framework for pneumonia detection with clinical report generation and model error analysis. You may now begin your presentation.
Ma'am, am I audible? Hello? Hello?
Yes, Arya, you're audible. We can see your screen.
Hello everyone. Good afternoon. I am Arya Manoj Madbi from Vivekanand Education Society's Institute of Technology, Mumbai. Today, I am going to present our research paper titled MedExplain, a hybrid explainable AI framework for pneumonia detection with clinical report generation and model error analysis. This research was carried out under the guidance of Dr. Shanta Sundur, along with my teammates Ajinkya Patil, Sushant Tulsi, and Sujal Tekwani. This presentation covers research problems, objectives, methodologies, findings, implementation, results, research claims, and finally the conclusion along with future scope. MedExplain is a hybrid explainable AI framework designed for pneumonia detection from chest X-ray images. This framework combines four main key components. First, that is a CNN-based detection model. Second, sharp explanations. Third, VIP-based interpretability. Fourth is a automated clinical report generation. The goal is to improve transparency, trust, and decision support in a healthcare setting. Chest X-rays are one of the important main used techniques for diagnosing pneumonia. While deep learning models can detect pneumonia with high accuracy, clinicians often hesitate to trust them because they do not explain why the decision was made. Our research focuses on making not only AI accurate but also explainable, transparent, and useful. From our literature review, we identified several gaps that motivated our work. Existing studies generally focus either on accurate pneumonia detection or on explainability. Very few integrated them. Our contribution is a hybrid system that combines all these components while supporting clinical workflows and future real world deployments. Okay, so starting with the first problem which we find out was that the AI models have black box nature, that is, they lack explainability. And the second problem which we went through is delayed and complex diagnosis. From these problems, we have come up to our primary objectives, which are first is to develop an accurate pneumonia detection model. Second is to provide SHAP-based explanations. Third is to generate clinical reports. And last but not the least is to improve readability and trust by analyzing false positive and false negative cases. This is the methodology which overall sums up our whole model. So starting with a user will input the X-ray given into a UI-based, web-based UI. Then that X-ray-based image will get pre-processed and important features will be extracted from that. Those important features will go into CNN models like DenseNet, EfficientNet, and then prediction will be made whether there is pneumonia or not pneumonia. Based on that predictions output as well as the image features, both of them will go into a XAI model where SHAP and VIT would work and generate an explanation of if of why that decision was made, and if not, so what are the features or what are the qualities to make that specific decision, or why the person has a specific disorder or specific results. After that, the report would get generated. That report, again, we have used some NLM-based techniques and compared that with original radiologist report and matched the accuracy scores. Here, we have used a dataset containing 800 chest X-ray images, where 400 were normal images and 400 containing pneumonia. We had divided it into 70% training, 15 for validation, and 15 for testing. The findings from our experiments were that MedExplain achieved a test accuracy of around 91%. Additionally, AI-generated reports achieved an average similarity score of 89.49%, with radiologist report indicating a strong clinical agreement. These are the results I have presented in a table form. Here, I have highlighted some representative clinical cases. In case 2 and 4, both SHARP and Vision Transformer and radiologists have reached the same conclusion, showing a great agreement. In case 5, represents a normal chest X-rays where all approaches that no pathology was present. But in case 1, it demonstrates why explainability is important. Although the AI predicted pneumonia with high confidence, the explanation differed from radiologist interpretation, allowing clinicians to question and verify their predictions. These examples show that explainability helps doctors validate decisions instead of blindly accepting them. Next, we have also evaluated the quality of report which we have generated using some NLP metrics like cosine similarity, birth score, and medical entity overlap. We have compared both the reports, and at the average, we have reached around 89.5% similarity score, demonstrating that generated report closely resembles with the except clinical documentations and reports. Here is the implementation which we have seen. This will be the generated report which we have created. And these are some of the false negative and false positive cases from our study. Next, from the following research, the research claim which we are making is that first, explainable AI significantly improves transparency. Second will be that Vision Transformer effectively captures pneumonia-related patterns and map them on the image. Third is that SHAP accurately identifies clinical features, relevant regions, and use them for explanations. Last, fourth is that explainability helps to detect false positive and false negative cases before clinical deployments. Finally, I would say MedExplain supports collaboration between AI systems and radiologists rather than actually replacing human expertise. Talking about conclusion, to conclude, MedExplain integrates CNN-based pneumonia detection, sharp explanations, vision transformers, interpretability, automated report generation, getting a 91% accuracy score and around 89.5% of matching score. As a future work, we can plan to extend these into a multi-disease chest X-ray diagnostic system, including diseases like COVID-19, tuberculosis, etc. We can also optimize it into a real-time explainability system and also integrate it into hospital, PAC, and DICOM system for real-world deployment. Thank you so much for your attention. I sincerely appreciate your time and would be happy to answer any questions or receive your feedback and suggestions. Thank you.
Thank you. Thank you. You have used CNN, correct? The
Hello.
CNN model. It's a
Yeah. So
CNN model,
basically,
right?
yeah. So our main focus was rather than like building CNN model was first part, but the main research and the main interest area was related to explainability, where we have explored sharp, line, and other different explainability techniques.
Okay,
And
fine.
yeah.
What is the size of your data set? From where did you collect your data set?
So basically, we have collaborated with one of a renowned hospital in Mumbai, and they provided
Okay.
actual patients' data set to us. We could not disclose which it is, but it was a
Very good.
real data
It's
set
a real-time
on
data
which
set.
we have.
Okay.
Yeah.
How did you normalize the images?
So we used different techniques, and so basically we got images which were in a proper format already. Then we
Okay.
used different
You got
techniques
all
like
pre-processed image.
no, we got normal image, then we pre-process and extract different features like the ages and the contours of that image. Then some images had some lungs and shape structure differences, texture patterns, opacity. So we use these techniques
Okay.
and normalize them.
Did you check your output with the doctors?
Yeah, we had actually whatever results we would get, we would send it to our mentor, and our mentor would talk or have a conversation with doctor, and then they could tell, okay, this is what you can improve and this is what you can. So it was like a collaborative process and incremental process.
Very good. All the best.
Yeah. Thank you, ma'am.
Hi, Neha. I request you to please pause your presentation. We'll introduce you and then you can begin.
Good evening.
Yes, Neha. Could you please turn off your presentation? We'll just introduce you and then you can begin.
Okay. I'm Neha, and today is my.
I'll introduce you. Don't worry.
Okay.
All right. Thank you. All right, yeah. So next up, we have Neha Chabra, who will be presenting IoT-enabled automotive performance monitoring and driver behavior analysis using ELM 327 and big data analytics. Neha, you may now begin.
Sure. Good evening, everyone. As my topic is already told by her, it's IoT-enabled automotive performance monitoring and driver behavior analysis using ELM 327 and big data analytics. So today I'm covering the introduction of my paper, LR proposed system, methodology, results, conclusion, and further references. So, so first of all, I want to give the introduction what I'm doing in this paper. We are having a device which is known as OBD, that is onboard diagnostic tool, and we are using its version 2. In earlier times, the vehicles, if facing any problem, they have to be monitored by the technicians only. But as the world is evolving and we are having so many technologies, so many sensors are used for collecting this type of data. Sometimes many drivers fail to monitor the vehicle health, which further affects the efficiency of the fuel, life of the engine, and also affects the safety of the vehicle. In this paper, we are proposing a big data analytics framework which uses the OBD second system, which further assesses the vehicle data through a 16-pin diagnostic link connector, which is also called as DLC, using an ELM327 adapter. We will connect this ELM327 OBD connector into a Hyundai Creta car and collect the live data in the form of CSV file. The goal to collect this data is to further collect the feedback from the drivers so that the efficiency of the vehicles can be enhanced. Further, it helps in providing the warnings and efficient driving. Basically, OBD second was the device which was developed by the car, and it is used for vehicle diagnostics by connecting it to the ECU. ECU is engine collection unit. It is basically used for collecting the fault detection in real real vehicles. We will apply the ML models on this using IoT and propose a model which will further help in driver behavior analysis and providing safety to the vehicles and the peoples, and helps in road prevention, accident prevention also. This is the device which I'm talking about, ELM327 OBD second scanner, and it will be connected in this DLC. This is a 16-pin connector, and there is an app which is known as car scanner app. The readings can be monitored through this app. So basically these three helps in collecting the data of the vehicles: OBD second scanner, this OBD scanner application, and this 16-pin connector which is present in the cars. For our paper, we have collected the data in a car which is Hyundai Creta. This is the LR. Earlier, this device was developed in 1991. Then the OBD second connects the vehicle's ECU to the OBD connector for data exchange. Excuse me. For data exchange and its diagnostic. Further, it was used for diagnosing behavioral analytics enabled by low-cost Bluetooth and adapters and smartphones. It will collect the OBD second data collection, IoT gateway architecture, big data processing, and machine learning applications for evaluating the performance of the vehicle and the driver behavior. Further, machine learning has improved OBD second systems by enhancing the efficiency of the vehicle, providing safety and the emissions control through different models for providing fuel optimization, driver behavior analysis, anomaly detection in any vehicle, and providing cybersecurity. In this paper, we have proposed a model which generally consists of 3 layers. First is data generation layer, next is data capture layer, and last one is data analysis layer, which further constitutes of several steps. In the first layer, data generation layer, it constitutes the vehicle. It gives the detail about the vehicle in which the experiment is performed. Next is data capture layer, the hardware which is used for connecting in this car, Hyundai Creta car, that is a ELM327 Bluetooth OBD second scanner. And last is the data analysis layer, which is a software one. It constitutes various steps like data collection, pre-processing, feature selection, ML models, data visualization, and system output behavior. I'm telling you all the steps in detail. In data collection, we will connect, as we have collected the ELM327 Bluetooth OBD second scanner in Hyundai Creta car, we will collect the data in the form of CSV files. Next, this data will be pre-processed so that we will, as we have collected raw data, we will pre-process all the data. After that, we will select the important features from that particular data, and if there is any redundancy, that can be removed. After that, various ML models like random forest, etc. will be applied. Next is data visualization. We have plotted various graphs, etc. And last one is the system output behavior. What we have observed, which type of behavior is observed from the of the driver by the this device. It may be aggressive, safe, or eco-friendly. Next is the data collection is done for 15 weeks. 15 weeks of driving data is collected from this particular device using this OBD second data. And this we have divided this 15 weeks into two phases, phase A and phase B. In phase A, we have trained the data in which we have collected the week 1 and week 2 data, and average fuel efficiency which was observed is 12.5 kilometer per liter. Next is phase B, in which the data from week 3 to week 15 is collected, which helps in providing the IoT-based feedback system, which further helps the vehicles for smoother acceleration, reducing idleness, providing stable throttle control, and helps in improving the average fuel efficiency to 14.1 kilometer per liter. What we have done, how we have calculated the fuel efficiencies, here the formula is given: total distance traveled divided by the total fuel consumed by that particular vehicle. In this, we have observed so many features like noise, missing data, handling signal losses. Sometimes the signal may be lost as the mobile app may be disconnected sometimes. Next is data cleaning. Many filters are applied which helps in removing the reliable data sets from the vehicle. Next, the last one is the threshold filtering. In this, incorrect readings are removed, and as they are in the form of outliers, they are removed from this particular data. These are some of the graphs which we have plotted from as the device has collected so many parameters like speed, RPM, throttle position, acceleration, etc. So these are the graphs which we have collected from, which we have made from the data. First is speed versus RPM. Next is throttle position versus RPM. RPM is rate per minute. And this is engine load versus speed, idle time in which the vehicle was not moving at all versus RPM, vehicle speed versus cumulative air intake. Next is intake air temperature versus RPM. So these are some of the visualizations which we have made from the data. Next is conclusion. By proposing this methodology, we are developing a low-cost IoT-based vehicle monitoring system using an ELM327 OBD second adapter with 15 weeks of Hyundai Creta driving data. It helps in providing an analysis which shows a strong relationship between driver behavior and the performance of the vehicle. It provides the behavior of the driver in the form of aggressive, safe driving, etc., and helps in providing the major factors, reducing the major factors like fuel efficiency, etc. Further, the system promotes the smart driving through real-time feedback, improving fuel efficiency and vehicle performance. It integrates GPS to identify inefficient routes and also optimize the travel of the person. In this, we have applied machine learning algorithms for predicting fuel consumption before trips. It also helps in enabling cloud-based real monitoring for remote vehicle and fleet management. Future work proposes that we can include GPS for finding inefficient routes using ML models for predicting fuel consumption before a trip starts. Further, it also helps in transferring real-time data to the cloud, which also allows the owners to manage their fleets from anywhere in the world and can have access to multiple vehicles at the same time. These are the references. Thank you.
Hello, ma'am. Good presentation. What is the role of big data in this entire work?
Sorry, ma'am, your voice is not audible.
What is the role of big data in this work?
Role of data?
Big data. Your title says it's on big data, correct?
Ma'am, it's IoT-enabled ELM327 device.
So I think I saw the keyword called big data.
No, ma'am. We have applied ML models and we have used this IoT-enabled automotive device in this
Okay, fine. You have concentrated only on random forest, no other model you have checked it?
Sorry.
You have used only random forest?
Ma'am, in this paper, we have done analysis only. We are planning to use random forest for further work.
Okay, thank you.
Okay, thank you so much, ma'am.
Thank you, Neha. You may stop presenting. All right. We'll circle back to the initial presentations that had been missed. Our next presenter will be Vedant Kaushik, who will be presenting a multi-tier hybrid architecture for efficient and explainable DDoS detection using ensemble learning. You may now begin.
Hello everyone, am I audible?
Yes, you are.
Just a sec. Yes. So is my screen visible?
Yes, it is.
Okay. So I'm Vedant Kaushik, and this paper is co-authored by me and my professor Dr. Chirag Joshi, and I'm representing Manipal University, Jaipur. So just a sec. Oh, yeah. So the modern DDoS detectors apply heavy machine learning models uniformly to every packet of network traffic, even traffic that's obviously malicious or obviously real. Real computational cost gets spent analyzing flows a simple rule could have caught in microseconds. Basically, what this says is we don't need to apply those heavy computationally expensive ML models to basically detect few DDoS attacks. Like our approach has this like a few filtering system which reduces this computational cost drastically. And about the existing approaches, most of the existing approaches, they are adaptive, but they fail at high false positive rates. And our ML uniform approach is the reason, like, we have very low computational cost. So our approach is a four-tier filtering architecture. The first tier is basically a rate filter. For every DDoS packet, a rate that is more than 1,000 packets per second, we would just filter it out. And about the second filter, for every volume, like if some if some if an attacker attacks our server with more than a lakh total packets, it would be dropped. And about the burst filter, if someone burst put attacks our servers for from tiny bursts like 30 packets worth 1 second, that's clearly an anomaly and we will have to drop it. And now for our final approach, the ensemble ML approach, that's the that's the part where like the only limited amount of data gets transferred to, and so its cost is very low. And about our ensemble approach, we are using three as written in this: MLP, RF, and XGBoost. More on them in later in the slides. Okay. And about our data set, we have used two data sets. One is Hornet 40 and other one is Kyoto 2016. The reason for using two data sets was clearly because Hornet 40 was not enough for the real-time data sets. Hornet 40 is a very renowned data set in for for capturing the data across different geographical locations of different honeypots. But it has few things that it only contain attack traffics. That's why we used Kyoto 2016, and it's a data set we are using just for its real world simulation capabilities. As for the combined data, it contains around 35,000 rows. And so let's look into the pre-processing which was done on these combined 35,000 rows. First, we applied smooth synthetic minority oversampling. And that was clearly because in Hornet 40, there were few attacks that were in uh, less quantity than other attacks. So to in order not to overfit our model, in order to train it perfectly, we are using smooth. About the feature scaling, it's basically for the fast computational purposes that we compute, we scale all the data into single space. It's basically a unit variance. Together, they give a balanced representation of both attack and normal scenarios, essentially for a model that must work in real world and not just on paper. About the SHAP, it tells us exactly which features actually matter. Like there were 14 features on the combined data set, but on SHAP analysis, it was found that only 7 of them were really useful. Like flow duration was one of the features that did absolutely nothing. Like sh- and like as you can clearly see that on 14 features there were 92% of the accuracy, and on the 7 features, when the model estimated it more perfectly, it it spiked up to more than 4%. So it was the fuser has better features and higher accuracy, so it's a less compute there in lower features. And about the three models I said earlier, the MLP, the random forest, and the
Vedant, sorry to
XGBoost.
interrupt. Vedant,
Okay.
I think your screen is not visible. Can you share it again?
Oh, it's not visible. Oh, let me just. I
Yeah,
think
it's
it
not
must have
visible.
been. Is it visible now?
Yes, Vedant. Yes, pa.
Oh, oh. So do I repeat from the past 2, 3 slides, or can I continue from here only?
No, no, you continue. You continue. You continue from the current slide. No problem.
Okay. Okay. So about our three models approach, we have used the MLP, the multi-layer perceptron, or we can call it just the deep learning, like a multi-neural network architecture, and a random forest and the XGBoost. And all three performed very good individually. Like MLP performed 96.45, and random forest performed drastically, like 99.95% accuracy. But what we are doing is we are soft voting the ensemble into 99.77%. Soft voting here basically means that we are averaging the three. The reason for not using only random forest or any other specific model was clearly because any model would have blind spots that they could have missed. That was the only reason to use three models combined. And about the output, it produces a multi-class classification model, and there are 4 classes which are being output in this model. One is the normal, the SYN floods, and HTTP floods, and UDP floods. About the SYN, HTTP, and UDP floods, there are 3 different form of attacks which were present in our Hornet 40 dataset. Uh, so about our full pipeline, the 4-tier pipeline, like estimated around 99.77% accuracy, and there are few false positive and few missed attacks. It's much clearer in this confusion matrix, where it's clearly seen that only one flow has been misclassified as an attack out of 3794 real real traffic, and only 2 attacks slipped through our total like 11,000 attacks. The reason for like these low false positive rates is also our major differentiator, because it's not like it's better if we block a normal user than to let a attacker pass. So that's why these number, like less false positive rates, really distinguish us from the past work. And about the past work that has been done, so as I said earlier, our false positive rates are really low as compared to other, and also our accuracy is really high. Like you can clearly see that all other models, they had like the moderate false positive rates, but they were not so good in those accuracy. And the other differentiator which I shared earlier was that we are only using ML on the data that has been pre-processed by earlier 3 filters. So our model is less is like the cheapest in the market right now, and it's a less computational model and has the lowest false positive rate. The reason for that was that it's like the speed of this, it's very fast because the the complexity of the first three filters is around O of 1. And about the major problem in the deep learning models is their black box model. But since we are implementing SHAP, it tells us which feature is most prominent in determining, like, is this an attack or not. And it's also scalable because it's cheap. I mean, with these RAM prices so high, I think the cheapest thing, like the cheapest computational cost I think is going to be the next future. And about the conclusion, it's adaptive, and it's deterministic filtering, and early stage filtering is what makes our system realistic for real-time deployment. And as per our limitations, evaluated on benchmark datasets, and so Hornet 40, as I said earlier, is a benchmark dataset and not on live traffic. And we focused on volumetric and known attacks. We could have gone for sleepy and low rate attacks, which are more common nowadays, but we are improving, and after this, we could extend our adaptive approach to involve more attack strategies. And for real-time deployment, for scalability and resilience testing, basically building a prototype for real users. And that was it from my side. And any questions?
Yes, with a good presentation. I have only one question. Both of your models, whether it is XGBoost and Random Forest, both are showing me 99.5% accuracy. Don't you think the model
Yes.
has become overtuned?
No. So the thing was,
Is
we
it
tested
overlearning
these.
or is it overtuned?
No, so in the training, in the actual code, we applied a few measures to prevent those overfittings, and also like there was SHAP, no, sorry, SHAP, the serialization, and it was a mix and SMOT, which all of these were applied in order to prevent overfitting. The model was overfitting earlier, but after applying those measures, it didn't overfit anymore. So it
Okay.
was in our version 1, we could say that, and then it changed after that. We applied Smote and Chaper.
No, without application of the methods for avoiding overfitting also, it was showing you 99.5% before also.
No, no, no. It was like it was. I mean, it was around 99.99 back then, but it came down
Okay.
after that. So. Hmm.
It has come down to 99.5.
No, but it's more trustworthy now and more scalable because we
See,
don't want our
normally what
system
will
to
happen is
fail or scale.
normally what will happen is when we have our own pre-processed synthesized data, these models will show me 99.5. But when I go in for a
Yes, yes.
real-time data applications or real data, it will go to 70s. So only I was just concerned whether you have done the measures for overfitting. Okay, good. You have anyway taken care of it. Good job.
Yeah. Thank you. Thank you. Thank you. Thank you, Anupama.
All right.
Yeah.
We'll now move on to the next presentation. Our next presenter will be Srishnav K, who will be presenting Adaptive Zero-Day Threat Identification with Unsupervised Machine Learning for Robust Cyber Defense. You may now begin.
Good evening, respected panel members. I am Srishnav K, and my other two co-authors will be presenting the paper ID 456. Tanvi will be starting with the slides.
Hello, am I audible?
Yes, you are.
Okay, just a minute. Can you see my screen?
Tanvi, I'd request you to please speak up a little. Your voice is very feeble.
Is my screen visible?
Yes, it is, and you're audible better now.
Okay, fine. Okay, good evening, everyone. Thank you for having us. My name is Tanvi Menon, and along with my teammates Shrishna, Harinath, and Akshata, we are from the Department of Computer Science and Engineering, specializing in cybersecurity at Dayanand Sagar University, Bangalore. Our project was carried out under the guidance of Dilip Kumar Jang Bahadur Saini. Today, we are presenting our research paper ID 456 titled Adaptive Zero-Day Threat Identification System with Unsupervised Machine Learning for Robust Cyber Defense. We have called the system Sentinel Zero. Let's see with why this matters. A zero-day vulnerability is a weakness attackers exploit before anyone even knows it exists. Traditional security tools, rule-based system, signature matching only catch what they have already seen before. So when something genuinely new comes along, it slips right through. We identified three specific gaps in the existing systems. First, the detection gap. Unfamiliar attacks go unnoticed because systems only look for known patterns. Second, the mitigation void. Most ML-based tools don't have a safe way to actually stop the threat without disrupting normal traffic. And third, the verification gap. Anomaly detectors tend to cry wolf, generating so many false alarms that security teams start ignoring them. Our motivation was to close all the three gaps in one system. Now, how this has been approached before, supervised deep learning models like CNN, RNNs perform really well on benchmark data sets, but they need huge amounts of labeled attack data, and they fail the moment they see something new. On the other side, unsupervised approaches like autoencoders and GANs don't need labels, but they are computationally heavy and unstable to train. So neither extreme was good enough on its own. We need something that combines the strengths of both worlds with a way to keep improving after deployment. Looking at the literature, we saw the same pattern across supervised, unsupervised, and even ensemble models. Ensembles improved robustness, but they still relied on static thresholds, which means high false positives the moment network conditions change. The gap, the fixed threshold problem, is exactly what we targeted. Now I'll pass it over to my teammate Akshata.
Hi team, I'll be continuing with system design, proposed architecture, adaptive sandbox quarantine. Tanvi, can you move on to next slide?
Just a minute.
Yeah. I'll be continuing further with system design. Here in our system, we have built in three layers. With each layer has its own responsibility. First layer being Engraze layer. Here, a smart gateway that conducts basic packet validation and it filters out obvious noise. So, like starting itself, all our validation is done before anything enters our system. Next, moving on to detection layer. This is our core project. Our main project lies here. Any traffic that looks suspicious, it is redirected to sandbox quarantine environment where the deep analysis is done using AI and Ensemble. Moving on to mitigation and feedback, instead of making every decision automatically, like tagging it as a red flag or anything, there is a human in the loop, security analyst who analyzes everything. Just like not only depending on AI, the human also like analyzes everything, analyzing if it is true positive, false positive, true benign, and everything, and gives the proper feedback. Next, moving on to methodology, end-to-end processing pipeline. Here, I will walk you through our pipeline, starting from data set to visualization. First, we'll start off with data set. We have used NSL KDD data set. It is our benchmark data set widely used for intrusion detection, research, and everything. Next, moving on to pre-processing. Here in our pre-processing, we make sure that we have cleaned everything, all the inconsistencies and everything, and we normalize everything in the pre-processing. We like convert everything into a similar data set. Next, moving on to feature engineering. This is where our PCA, principal component analysis, comes into picture. Fine tuning happens here. We keep like important features and remove redundant information. We like basically the fine tuning happens here. Next, moving on to model training. We trained our unsupervised learning models, K-means clustering,
which learns the patterns of normal network behavior by grouping similar traffics together. And then moving like for isolation forest, it detects the anomalies. Anything which deviates from the baseline, isolation forest detects it. Next, moving on to prediction, the anomaly scores from both like the previously mentioned K-means cluster and isolation forest. It combines and gives us the anomaly score, fusion score, which is compared with our dynamic threshold. We keep updating ourselves, like the system, it compares with itself. Next, moving on to threat analysis, here where again the human in the loop comes into the picture. The security analyst makes sure that everything is proper and it goes on systematically. Moving on to visualization, the final results are displayed on SOC dashboard, allowing security teams to monitor the alert, analyze threat, and make like informed decisions in real time. Next, the working will be taken forward by Shrishna.
Hi, I will be demonstrating the live working of our software, Stencil Zero. Yeah, this is our this is our software Stencil Zero. The name only shows as we are seeing the thread or thread all that thing. This is our working means software. Before I will demonstrate our project, I will show the visualization how it works. See, this is our idea from where the we made a sandbox environment in between the two internet and the server. Here our software will be working. We saw the proxy, the server in proxy server, which we are seeing that blue packets going to the main server. The server registered, direct registered means XYZ company. We already given the XYZ company or something or else company. So all that packets of that XYZ company will be going directly. But unauthorized means those who means other from the XYZ company packets, it will be went to our sandbox environment, which where our ML will ensure that it is there is any issue or any something any threat is identified or that thing, and then it will, if it's okay, it will go to direct server. If it's not, it will go make it to go to quarantine, and we will check it. Second verification is human verification. Then I will start saying downset the working. As we do the initiate scanning, we can see the threats are going detecting. Yes, threats are starting detecting. As we go to quarantine bay, the attacks, we can see what all are attacks going on. The forensic attack is going on, at which port it's going attack, the port full all details and the location. Now this location will be not accurate because as we are doing in a closed environment in Kali Linux and Metasploit. So now it's our software is going in a testing phase, so we can deploy it as so location will be not accurate because the attacking will be accurate because I am only initiating the attack, all that thing. I am only doing the attack. So
Excuse me, I'm sorry to interrupt. You have a minute left.
yeah. Then we'll from here we can if the risk is very less, if it is 15 or 49%, so I can authorize it. Can go to see the 82%. More than 50% will be neutralize it. All that thing will be the 42%. Again, it's 42. It's less than the prescribed percentage level. All that thing. Then the all risk is identified according to the this all geolocation and the ports where it's going to attack, all that thing. This three are the matters we are seeing. The packet size. If on one same server means port, so many attacks are going on, so we'll be neutralizing that thing. All that, and in intelligence way, we can see how many attacks have been done, how many packets are scanned, and all that thing, all the attacks, and where it is coming, where which location. I already told location will be not mentioned here because it's in closed environment. And if after the FTP host, we can see all the from where the proper attack is coming on, all that thing. The traffic now it will be zero only because it's in quarantine way. That's all. Thank you. That's all.
Good work from all of you. And you have shown me the live video of your working, live experiment of your work. Very good. Now, you have told me that you have used one data set from KDD, correct?
NSL KDD, NSL KDD, and zero data.
What are the features you got in the data set?
See, NSL KDD, there are already, means in NSL KDD, there are already some attacks and all that thing will be there. So we'll be using that data set to see that if that matches to the same, means there will be some attack factors, to same port, so many attacks are bombarding. So it will be see, is this attack and that the data set I have given is same. Then it will match, like in matching the tables, right? They will match this attack is same. So it is, then they will match it, then it will be go to our quarantine, then the second verification is by human, then only it will be then I can say it's see I've shown that it's showing 46%, 40, 50. The percentage will be determined on the data set I have given.
Okay, very good presentation, good experiment also.
Thank you. We have another presenter left who was previously absent. We'll just check if any of the co-authors are present today. So our next presenter is Rahul Dhaigade. If Rahul or any of his co-authors are present today, please let me know. All right. In case they're not, we'll move towards the closing remarks. So I sincerely thank all of our authors for their excellent presentations and contributions in this session, and all of our participants for being a part of this international conference. I hope the session was informative, and on behalf of the whole team, I thank you for your support during this 11th version and all the previous 10 versions of the conference. We will be happy to have you in the 12th version as well in 2027. All the presenters will be receiving their digital certificates via email within the next 2 working days, and the publication will be live in 7 to 8 months. Kindly cooperate with the team of ICT4SD 2026. Before we conclude, I would like to thank our session chair for chairing this session, and a token of appreciation to the chair on behalf of team ICT4SD 2026 and Global Knowledge Research Foundation and partners is being presented. Thank you so much for your valuable presence, ma'am.
Thank you. All the best, participants. You all have done a very good job. Keep doing research. It's very good for the society, also for your benefit also. All the very best.
Thank you, ma'am.
Thank you.
Before we end the session, I would like to request everyone to please turn on their cameras for a quick virtual snapshot. All right. Thank you so much. The session is now concluded.